Hi, my name is Melissa Micah. This is Regional Precipitation Frequency Analysis. This video is Part 5, Regional Frequency Analysis Applications. In this video, we're going to talk about a few applications related to performing a regional frequency analysis, starting with data considerations, NOAA Atlas 14 as a data source, performing storm typing, and then lastly, stochastic storm transposition, which is a special type of analysis similar to regional frequency analysis. We'll start out talking about data considerations, specifically when using precipitation data for regional frequency analysis. Previously, we talked about some of the key differences between regionalization of streamflow versus precipitation. To summarize this, streamflow represents an aggregation of the entire hydrometeorology for the watershed above it, whereas precipitation represents measurements at a single point. Streamflow records have a longer memory, or a high serial correlation, which means that flows that happened in the distant past and the near future are more related to each other. This isn't the case for precipitation, which has a low serial correlation and is due to the chaotic nature of meteorology. Streamflow also has typically a single source of data in the United States, which is from the USGS. The USGS also performs meticulous quality control on this data. In contrast, precipitation data can come from many different sources. This means that not only is the formatting and reporting of the data different, but there's also inconsistencies in the quality control or whether quality control is performed at all. This is the piece we're going to focus a little more on in this video. A problem that we've identified that exists more so for precipitation than for streamflow is the possibility for incorrect or erroneous data. When you encounter values that don't seem to make sense, a healthy dose of skepticism is a good thing. There are many ways that precipitation data can be incorrect. While many precipitation gauges are now automated, most gauges prior to the 1970s used to be manual. This can introduce possible errors when transcribing data from paper forms to digital forms. There's also the possibilities for sensor malfunctions or misreporting. Some of the sources of precipitation data come from volunteer reporting, which also have the possibility for error, etc. It's up to you as the analyst to determine whether the precipitation data is of acceptable quality or not. Detecting errors requires some testing. While it's good to start by looking at the plot of data visually, there's also some statistical tests we can perform to check for data quality. Most busts occur in the large direction. This doesn't necessarily mean that only large observations are subject to error, but large values are likely the only errors we will be able to detect. Large errors also would have the most influence on our regional frequency analysis. For this reason, we typically focus the quality control on the annual maximum series, since that's what we're ultimately most interested in. It also helps because regional frequency analysis must collect orders of magnitude more data than when performing a site analysis. Some of the most common statistical tests that can be performed include largest observation ratio test, which is where the largest and the second largest observation are compared to a threshold. Next is the outlier test, where all values that fall above or below a specific threshold are flagged for inspection. The threshold is typically 1 or 2 standard deviations from the mean. Next are trend tests, which can look for non-stationarity in the data. And finally, extreme L-moment ratios, where the site's L-moment ratios are compared to other sites in the adjacent area, and extreme differences are flagged. There's many more statistical tests that can be performed, but these are some of the most common for precipitation data. Missing data can occur quite frequently in precipitation. The problem is, if a year has many days of missing data, it becomes less and less certain whether the observed maxima is the true maximum or not. This chart is kind of a rule of thumb to help determine what to do when you have missing data. We both consider the percent of the year missing from 0 to 100% of the year missing, and we also consider the magnitude of the maximum. Years where there is very little missing data, we will typically keep. And this is typically if there's less than 5 to 10% of the year missing. If there's a high percent of the year missing, but the magnitude of the maximum is low, then we usually reject that value. If there's a low to moderate amount of the year missing, and the maximum is relatively small, we typically reject that value with little consequence to the analysis. Simply stated, since the magnitude of the maximum is so small, it's unlikely to impact your analysis. These two areas are a bit more difficult and subjective and often are a case-by-case decision. Large values are very important to the analysis, and so we might be more likely to keep them even if some of the year is missing. These case-by-case values could also be corroborated by nearby gauges. There are no hard and fast guidelines for this, but typically if an observation is above the median, then we would consider keeping it in the analysis. To look at these concepts a little more visually, this is a calendar year 2016 for precipitation gauge near Spencer, West Virginia. This gauge has 0% of the year missing. Keep your attention on this annual maxima here, which happens to be one of the largest events in the entire period of record for this gauge. Now pretend we have the same calendar year, but 48% of the data is missing. You can see it would be hard to draw a conclusion as to whether this peak is the true annual maxima or not. For this reason, we would likely reject this year from the annual maximum series. Now the calendar year only has 4% of the data missing. We would most likely keep this year in the annual maximum series because this is an acceptable threshold of missing data. Now the year has 16% of the data missing, but it does include one of the largest measurements in the gauge's entire period of record. It would be a shame to miss out on a large measurement like this, so we would most likely keep this year in the annual maximum series. And finally, this also represents 16% of the year missing, but it no longer includes large annual maxima. Since none of the observed values are significantly large compared to the rest of the record, we would likely reject this year with little consequence to the analysis. The last topic I want to discuss with regards to data is a concept called constrained observations. This is an artifact of how we typically collect precipitation data. We typically use analysis periods such as 48 hours or 72 hours that are agnostic to the calendar day. However, precipitation data that's daily tends to be collected on a calendar daily basis, such as at midnight or at noon each day. This plot on the right shows a time series of precipitation data with daily precipitation in blue and hourly precipitation in purple. If we were interested in the 3-day maximum from this plot, we might extract 2.54 inches. However, now, using the hourly precipitation, let's extract the 72-hour maximum, which comes out to be, in this example, 2.78 inches. This highlights the problem with collecting daily precipitation data is that it's typically smaller than would have been observed if we were using hourly data. For this reason, we typically apply a constrained observation adjustment when we're using daily precipitation data. This adjustment factor is typically calculated using observed data from hourly precipitation gauges. For this example, it's comparing 3-day annual maxima to 72-hour annual maxima, and this would need to be repeated for each duration of interest. The constrained observation adjustment will always be a positive value close to 1 because the hourly accumulations are always larger than or equal to daily accumulations. Next, we'll talk about NOAA Atlas 14. NOAA Atlas 14 is a precipitation frequency estimate and is the standard source of this data for the United States. The top right figure shows the different volumes and their availability in each state. NOAA Atlas 14 is a regional precipitation frequency analysis, just like the steps we talked about in part 4 of this series. However, since this is a more national and not a site-specific analysis, there are some limitations. The first limitation is that NOAA Atlas 14 estimates only go up to the 1 in 1,000 year event. This can make it difficult if you need to extrapolate to values beyond 1 in 1,000. In that case, you would likely want to perform a site-specific regional frequency analysis like we talked about in the previous videos. Additionally, some of the volumes in NOAA Atlas 14 are a bit outdated, such as Volume 1 and Volume 2, which are over 10 to 15 years old at this point. Currently, not all regions are represented in NOAA Atlas 14, specifically the Pacific Northwest. And finally, since this is a national level analysis, the regionalization process receives a little bit less scrutiny. I will note that some of these limitations are soon to be overcome because NOAA is working on developing Atlas 15, which is going to be a national scale analysis, and I'll talk about that more in a couple slides. NOAA Atlas 14 data is available from the Precipitation Frequency Data Server. It contains estimates for a point selected by an address or a single location on a map. In addition to the point frequency estimates, you can also obtain rasters specific to an annual exceedance probability and a duration, such as shown in the web server to the left. You can also obtain time series of annual maximum series and partial duration series from the precipitation frequency data server shown here. These are the data that were used to develop each volume and can be a very helpful starting point if you don't have the time or capacity to collect your own precipitation data and perform quality control. However, keep in mind many of these datasets could be 10 to 15 years old at this point. I mentioned NOAA Atlas 15, which NOAA is currently working on developing. Atlas 15 is both updating the estimates from NOAA Atlas 14, and it's a national scale analysis which will include all of the United States. Next, we're going to talk about a concept called storm typing. When performing regional frequency analysis, we typically define our homogeneous regions as those that are subject to a similar set of meteorology. Sometimes we may wish to separate out different storm-producing mechanisms or different storm types. This is commonly done for mixed population analysis, which we talk about in some of our other lectures in this class. In brief, storm typing is where meteorology meets statistics. There are 4 general types of storms in North America: the mid-latitude cyclone, the tropical cyclone and tropical storm remnants, mesoscale storm with embedded convection, and local storms. This plot on the left is very helpful to visualize different types and scales of storms. On the y-axis, we have seconds, which shows the time scale of different types of storms, ranging from minutes to hours all the way to years or multiple years. On the x-axis, we have meters, which represents the spatial scale of different types of storms. To help put it in perspective, this is approximately where the width of the United States from coast to coast would fall. Mid-latitude cyclones and tropical storms are considered synoptic scale. These are the largest spatially and temporally, which can cover over 1,000 kilometers at a time and typically last multiple days to weeks. Mesoscale storms with embedded convection, or MECs, are at the mesoscale, such as frontal storms. The typical duration for these types of storms is around 6 hours, but it can be longer or shorter than that. Finally, local storms represent locally intense thunderstorms of very short duration and small spatial area. These are typically analyzed on a 2-hour duration and generally do not contribute to the record of the most extreme events. We can perform storm typing by assigning one of these general storm types to each annual maxima in a gauge record. Storm typing has 2 general benefits for the precipitation frequency analysis and 1 major benefit for the application of the findings. First, when you're regionalizing by a storm type, you can draw on an even larger regional basis as long as the predominant storm type exists in that location. This helps draw on even more data when performing the analysis. Second, samples drawn from a single storm type are homogeneous. This decreases the prevalence of mixed populations in your dataset, and more homogeneous time series tend to work better with classical extreme value theory. Finally, a benefit when applying the data is that frequency estimates can be combined with spatial and temporal patterns for that specific type of storm. The downside is storm typing is a fairly resource and labor intensive procedure. There is an important connection to make back to extreme value theory. When we make sure our populations are homogeneous and not mixed, their properties can be reliably predicted with extreme value theory. This aids us in choosing the right probability distribution for these extremes. The graph on the right shows different contributions to the uncertainty for various annual exceedance probabilities. The selection of regional probability distribution is a large portion of the uncertainty, especially as we get to more extreme estimates. So improving our confidence and selecting the probability distribution by using storm types, we can effectively reduce this uncertainty. Lastly, we'll talk about stochastic storm transposition, which is a special type of analysis. In the previous videos, we talked about performing regional frequency analysis for precipitation data. The key idea behind stochastic storm transposition, or SST, is what if we were to regionalize spatial and temporal patterns of storms instead of just the annual maximum data. The general process for SST is to first determine a homogeneous area, which would be called the transposition domain, and to build a large catalog of independent storms that have been observed in that area. We would typically use gridded precipitation that represents both the magnitudes and the spatial and temporal distribution of the storm. Next, we would take those observed precipitation grids and randomly transpose them in space to a different location within the domain. In this way, we can simulate the natural variability of precipitation that could result at a location of interest. As I mentioned, the storm catalog would come from a time series of precipitation rasters, or grid data. The figure on the right shows the extents of our transposition domain, or our area of interest. We then transposed all of the storm events in the record to maximize the precipitation over our watershed of interest. We then keep all of the largest events that fall above a specified threshold, and this becomes our storm catalog. This would be considered a partial duration series rather than an annual maxima. Once we've developed a storm catalog, the procedure for actually performing SST simulation would be to randomly sample from the catalog, that is with equal probability, transpose the storm center to a random location within the domain, and compute the watershed average precipitation or apply the precipitation to a hydrologic model. We would repeat this many times to represent the number of storms that occurred in a single year. This number is typically determined using Poisson distribution. Then, the above steps would be completed many times to represent a realization of the simulation. So we would sample multiple storms for each year, and then we would sample multiple years. To compare SST to the traditional precipitation frequency methods that we discussed in earlier videos, precipitation frequency analysis uses annual maximum of gauge data. We fit our data to parametric frequency curves. There is typically mild to moderate correlation between gauges that are very close to each other. We have to make many assumptions when applying regional frequency analysis, and the results represent point frequency estimates, which would need to be adjusted based on areal reduction. In contrast, SST is based on gridded data. It uses a peaks over threshold approach. The simulation is non-parametric, meaning we don't have to fit a model to the data. The events are explicitly separate, so there's no issues with correlation between adjacent gauges. The application is more simplified, and the results are inherently area averaged. SST has a lot of benefits over traditional precipitation frequency, but the limitations are that it's much more intensive to develop the storm catalogs and perform the stochastic simulations. To summarize this video, we talked about different data considerations and how to perform quality control on precipitation data. We talked about NOAA Atlas 14 and the upcoming Atlas 15 as the standard estimates for the United States. We talked about storm typing and how this can be used for mixed population analysis. And finally, we discussed a different type of analysis called stochastic storm transposition. This concludes video 5 of regional precipitation frequency analysis. Thanks for watching.